Okay, so now I want to continue talking about the limit, and it should be the last video about limits. So I have three things to discuss. So the first thing is the squeeze theorem, and it's actually not too hard to just prove it. So maybe we'll just see a proof of it, and also we will need to know how to use squeeze theorem, how to apply this into solving problems. And then we'll talk about the two important theorems regarding continuity, regarding to continuous functions that are called the extreme value theorems and intermediate value theorem. So first, we will talk about the squeeze theorem. So it says that so for example, we are looking at a point which is called A. And then if we want to find the limit of this function at this point, and all we know is that we have two other functions. So one of them is, so let's say this is g of, let's say this red graph is g of x, and then the green is f of x, and then also let's say we have h of x. Okay. So if we know that for all x, at least for all x that are close enough to a, or we can just simply say that if for all x we have f of x is, so this is an assumption. Okay, we assume that for all x, or for x close enough to a, we have f of x is less than or equal to g of x, and also less than or equal to h of x. So this is kind of like a squeeze. I mean, and also we assume that the limit as x approaches a of f of x and h of x, like the green line, the brown line, will converge to a limit that is the same. And the squeeze theorem says that this will force g of x to have the same limit. Okay, so if we also assume that the limit of f and the limit of h at a are equal, and let's assume this is L. Okay, then it says the limit of g of x must also be L. And to prove it, you can use the epsilon delta proof. So we can simply prove it. So we can look at the epsilon neighborhood of L. And then because f has a limit that is L, which means we can find some neighborhood, let's say some delta 1. Okay? We can just let epsilon bigger than 0. So since the limit of f of x at this point is L, so then we can find, so we can have some delta 1 bigger than 0, such that for all x, if x is close enough to a, I mean if the difference is less than delta 1, then f of x, then the difference of f, or let me put it in this way, then f of x must be less than L plus epsilon and bigger than L minus epsilon, right? This is what I mean for the absolute value of f of x minus L less than epsilon. And also, because we have the limit as x approaches a of h of x to be L, that means we can also find some delta 2 bigger than 0, such that for all x such that x is close enough to a, when this difference is less than delta 2, then we have h of x is bigger than L minus epsilon and less than L plus epsilon. And now we want to find some delta for this g of x. Okay? So what is this delta? We want this delta to be very, very small, such that we have both conditions of f and h. So should we choose the smaller one or the bigger one? Here, the intuition is that this is true for all small enough x. So this means we should choose delta to be the minimum of delta 1 and delta 2, which means we choose the smaller one of them. And this is clearly positive, and because both of them are positive. And because we have choose delta to be the smaller one, now if we want to show that the limit is equal to L, then all we need to show is that for all x, if the absolute value of x minus a is bigger than 0 and less than delta, then we want to show that g of x is bigger than L minus epsilon and smaller than L plus epsilon. Okay? But how do we show it? Well, we just assume that x is some real number that is has distance to a less than delta. Then because delta is a smaller one, which means if this is true, then this absolute value is less than delta 1 and less than delta 2 at the same time, right? Because we choose a smaller one. So both conditions hold, which means we have two conclusions. The first conclusion is that this f of x will be within this interval. So it will be bigger than L minus epsilon and less than L plus epsilon. And also, this will be true for h of x. It is also bigger than L minus epsilon and less than L plus epsilon. And the point is that here, we can actually use this inequality because g of x is within f of x and h of x for all x, or at least for some small, some close enough at x to a. Then, this means we can actually form a longer inequality. So g of x will be bigger than or equal to f of x and bigger than L minus epsilon, and then less than or equal to h of x and less than L plus epsilon. Which means g of x is also within this interval, and we're done. Because then this shows that this shows that g of x is bigger than L minus epsilon and less than L plus epsilon. So that is a proof of the squeeze theorem. Okay, and this makes sense. So let's take a look at some examples when we can use squeeze theorem. So usually it's about the trigonometric functions. So for example, if we look at the graph of let's say sine of 1 over x, then this is clearly, then the limit does not exist for sure because it oscillates from minus 1 to 1. But what about x times sine of 1 over x? Okay, so we'll say that this function is f of x. Then if we look at its absolute value, which is the absolute value of x times sine of 1 over x, then this is equal to the absolute value of x times the absolute value of sine of 1 over x. And we know that the absolute value is bounded. It is at most 1, right? Because sine of 1 over x is bigger than minus 1 and less than 1. So if we take the absolute value, then it's always less than or equal to 1, right? This is less than or equal to 1, no matter what this is, because the sine of anything is at most 1. So then we will have that this entire thing is at most or bit less than or equal to the absolute value of x times 1, which is just the absolute value of x. Okay? So what does it mean? It means that f of x, if we remove this absolute value, then this will be bigger than or equal to minus the absolute value of x, and less than or equal to the absolute value of x. Okay? And now, if we want to take the limit as x approaches 0, then you can see this will approach 0 when x approaches 0, right? And this will also approach 0. So by squeeze theorem, this tells us that f of x must also approach 0. So geometrically, what is the graph of absolute value of x? Well, this is simply this graph, right? And f of x is less than or equal to that, which means f of x lies in this part of the plane. And also f of x must be bigger than or equal to negative absolute value of x. And this is negative absolute value of x, which means f of x must also be here. So this means f of x must be within this cone, right? I mean, or two cones, right? So f of x must be here. And you can see whatever this graph is, then locally at this point, or locally near this point 0, it must approach 0, right? So this is why the limit as x approaches 0 of x times sine of 1 over x will be equal to 0. Okay, so this is done by squeeze theorem. So, and by the way, you can actually you can actually sketch the graph, and I think it would be something like this. Okay, so you can see that it really approaches 0 when x approaches 0. Okay, and so in practice, I'll show you some examples. If you are asked to show that the function f of x times g of x, okay, the product of two functions at a point, let's say when x approaches a, is equal to 0, then one way to show it, so this is one way, is that you show one of them is bounded, which means the absolute value is less than or equal to some fixed number. And also you show the other function approaches 0. So without loss of generality, we'll just assume that f of x will approach 0. Is to show that the first, so one of them, let's say f of x, will approach 0 when x approaches a, and the other one is bounded, which means you can find some constant c bigger than 0, such that for all x, or at least for some close enough x to a, we have the absolute value of g of x is at most c. Okay, so in our case, in our previous case, this is the limit as x approaches 0 of x times sine of 1 over x. So in this case, x approaches 0, right? When x approaches 0, x approaches 0. Okay, but this is bounded because this absolute value is at most 1. You can see that we use this, right? We use this, so this bound actually is here. So if this is at most c, then this is c. But it doesn't matter because a constant times something that approaches 0 also approaches 0. So all we need is that this is bounded, or the absolute value is less than or equal to some fixed number. Okay, then we can show that the limit will approach 0. So let me first prove that this is okay. I mean you can prove it. So to prove it, it simply says that the absolute value of this is at most c times f of x, c times the absolute value of f, right? So this means if you remove this absolute value, then it will be bigger than or equal to minus c times absolute value of f of x. And then because f of x approaches 0, so the absolute value also approaches 0. And if you multiply by negative c, it also approaches 0. And this also approaches 0, so this must approach 0, right? So this is the proof. So let me give you maybe a more complicated example. So when x approaches 2, let's say, then x squared minus 5x plus 6 times cos of 1 over x squared e to the 3x minus 1 is equal to 0. Okay, why is this true? Well, this is because this is equal to x minus 2 times x minus 3. And then when x approaches 2, this will approach 0, right? Because this approaches 0, and 0 times anything is 0. So this limit is 0 when x approaches 2. And this is cosine of something, which is bounded, because this absolute value is less than or equal to 1. So then you can use squeeze theorem to show that the entire limit will be 0. Okay? But how will you show when the limit is not 0? Let's say this limit is some L. Then you simply subtract this L here, and then change this question into a question in the form when the limit is 0. Okay? So usually, when we prove, this is a common trick. When we want to show the limit is equal to something, we subtract this number to the left, and then we show some limit is equal to 0, right? So what I'm saying is that one trick is that whenever you want to show the limit of f of x is equal to some L, you can change this into the limit of f of x minus L, and you want to show this is equal to 0. Okay? So sometimes this will be very useful. So for example, later you will see that if a function f is differentiable at a point at a, then f is continuous, and then you will use this trick. Okay. So it's very, very useful, but here maybe you just take it for granted or just keep it in mind. Okay. So this is about the squeeze theorem, and then I will talk about the extreme value theorem and also intermediate value theorem. They are also theorems about continuous functions. So the extreme value theorem says that if you have a continuous function on a closed interval, let's say closed interval is things like this a, b, right? It's all the set of x such that x is bigger than or equal to a and less than or equal to b. So it has two endpoints that is attained in this interval, right? If it's open interval, then neither of the endpoint is attained. If it's half open, half closed, so here this is closed, this is open, then it means the left endpoint is attained, but the right endpoint is not attained. So in the case of closed interval, it means both endpoints are attained. In the interval. Okay, so now let's assume that we have, so if f is a continuous function on a closed interval, or we can say we can translate this to f is continuous on a closed interval. So things like this. Okay, things like this. Then, extreme value theorem says that you can always find some point that is the maximum of the function on the closed interval. So here in this case, you can find, for example, this, we can call it x star. Okay? Maybe we'll call it x1 and x2 for simplicity. So let's call this point, maybe we'll call it c, okay? Then we can find some c in this closed interval that is the largest. Okay, so what it means is that f of c is equal to the maximum of all the f of x where x is in the closed interval ab. But this can be abstract, so you can also think about this as you can find some c in the closed interval such that for all x in the closed interval, the value of f of x is always less than or equal to f of c, which means this is not less than any other value on this interval. Or we can say that, so this means the maximum of f, of a continuous function f on a closed interval ab is attained at some point. Okay, it is attained on some point, at some point. And the point is that it doesn't need to be unique. For example, it can be constant maximum for some point. The point is that it exists. Okay, we can prove that the maximum exists. And similarly, also in the extreme value theorem, we can also find some minimum. In this case, this is simply the left endpoint. Okay. So we can also find some d in AB such that for all x in the closed interval AB, f of x is bigger than or equal to f of d, which means the minimum is also attained. And these 2 points, like the maximum on the interval and the minimum on the interval, are called the extreme values on the interval. So that's why it is called the extreme value theorem. Extreme value means it's either maximum or minimum, at least on an interval. Okay? You cannot talk about maximum at a point, right? It makes no sense. It has to be a maximum on some interval or on some set. In this case, it's on a closed interval. So I will show you why we need it to be continuous and why we need it to be closed interval. Okay. So what I mean is that if I remove this condition that this is a closed interval, then I can find some counterexample so that even if this is continuous, it does not attain maximum or minimum. Okay? And then I will say if it is a function on closed interval but it's not continuous at least for some point, then it can have no maximum or minimum on the closed interval. So for the first example, there are counterexamples, but they are used to illustrate why we need it to be closed and continuous, closed interval and continuous. So the first counterexample is, so what if, so this happens when the interval is not closed. So not closed interval, or when the interval is not closed. Then let's say it's simply 0, 1, okay? And I will not assume neither of them attain in the interval. I just assume that even when the case that only one endpoint is missing, then this will cause problem. We will look at the graph of 1 over x. Okay, this is the graph of 1 over x. At least for we will focus on this part, 1 over x. We'll focus on the half open, half closed interval 0, 1. Then you can see 1 over x is clearly continuous on this half open, half closed interval 0, 1. Right? And it actually has a minimum, but it has no maximum, right? Because it will approach infinity. But it has no maximum. So similarly, if you choose it to be minus 1 over x, then it has no minimum, okay? So here, why the reason why it has no maximum is that the limit as x approaches 0 from the right of 1 over x is equal to plus infinity, okay? This will approach plus infinity. So it clearly has no maximum, okay? So this is why this interval must be a closed interval. Otherwise, you cannot say anything about the result. Otherwise, you cannot say anything about the extreme value, okay? Because, for example, if both of them are if it's open interval, then it can happen, for example, it's things like this. If you just define it in a clever way, then you can, let me put it in this way. So let's say, then you define it like here, okay? Then you can see neither, you can see it does not attain maximum or minimum. So maybe we can just look at, for example, arctangent, right? That would be a perfect example. So if we look at the graph of arctangent, so this is minus pi over 2, this is pi over 2. So then the graph would be something like this, right? This is continuous. So tangent is continuous on this open interval minus pi over 2 to pi over 2, but it is not, it has no maximum or minimum, right? So that's why this interval must be closed. The second thing is that we want it to be continuous. What if at least for some point it is not continuous? So this is when it is not continuous, at least for one point. So which means the second counter example is used to show that it is very important that it is continuous at every point of the closed interval. Like every point is important. So this is kind of a global property, right? It's global because every point matters, right? So I will give you a counter example. So it is defined on the closed interval. So it can be very, very silly, but let's take a look, like from A to B, okay? So let's just look at this graph. Okay, this is all good, it's linear. But suddenly at this point, it becomes smaller. And suddenly at this point, it becomes bigger. So you can see it should have the maximum attained at this point, which is this value. Let's say this is m. But it is not attained because it is made to be something smaller. And here, this should be, the minimum should be n, but you change the value slightly bigger such that the minimum is also not contained, right? So in this case, I mean, you can definitely construct you can definitely find some number, some a, some b, some linear function, and these 2 points to make this work. But I don't care about that. The point is that you can really find some function that is super weird when you ask it to be not continuous. And the problem is not only at the endpoints. So here the function is defined on closed interval, but it's not continuous. Here it's not continuous at A and B. Okay, and also you can have a million counterexamples. For example, from A to B, let's say this will go up and then go down. At this point, it's not attained. It becomes something smaller. Then the maximum is not attained. So you can see that the continuity matters at every point. Okay. So now let's look back at this extreme value theorem. It says that if we have a continuous function on a closed interval, then it can definitely attain its maximum and minimum on the closed interval. Right? We have to emphasize the maximum or minimum on some set, right? We cannot simply say the max. We have to say the max on this interval, or we can say the max for all real numbers, right? We have to emphasize what is the set that we are taking the max. Because, for example, I mean, for the good example, if say, let's say we're just looking at x, okay? Y equals x. Then the maximum of f of x equals x from on the closed interval from 0 to 1, the minimum on this interval is 0, and the maximum on this interval is 1. But this is only for the minimum and maximum on this interval, right? For the entire graph, it has no minimum or maximum. So you have to be very, very careful whenever you say maximum or minimum, because you have to emphasize the maximum on some set, right? Or on some interval. Otherwise, it makes no sense. Or it just, otherwise, I mean, this usually means for all real numbers, or like the global max or the global mean, or like the max for all the value in the domain, right? The max on the domain or the minimum on the domain. Otherwise, you have to emphasize what's the set, okay? So in the case of the extreme value theorem, the set is always the closed interval itself. Then I will tell you about the intermediate value theorem. Again, this is a theorem about continuous functions. And clearly from the previous example, we have shown that it has to be continuous everywhere. And so here it should be also continuous on the closed interval, which means it's continuous at every point of the closed interval. So I'll start with a simple observation. So if you have a continuous function, let's say at a on the closed interval ab, whose value at a is less than 0, so it's below the x-axis, and the value at b is positive, which means it is above the x-axis. And if we want to have a continuous function on the closed interval ab, that means we have to sketch a curve that join these 2 points. So you can see it has to pass this x-axis on some point at some point between a and b, right? It is because, right? I mean, if you don't want to cross this x-axis, then you cannot go to the positive value. Okay, so this is one of the clever observations. You have to pass at least once. So this is the simplest form of intermediate value theorem. So it says that if f is continuous on closed interval AB and f of A is less than 0 and f of B is bigger than 0, these are assumptions, then you can find some C that is in the open interval AB such that f of C is equal to 0. Okay? And by the way, you can use this simple lemma. I mean, if you want to prove it rigorously, it will take time because you have to use some like supremum or infimum. But in our case, we just take it for granted. Okay? This should be true, so it's true. If you are interested in the proof, then you can search online. There are literature about this. So using this, we can actually have a method to locate a 0. So let's say we have some function that is very, very weird. And then we want to find some 0. Then how should we find this 0? So one way to do it is that we can find some value A that is smaller than the possible 0, whose value is less than 0. And we have some B whose value is bigger than 0. And then we can bisect this interval AB. And then you can see the value here is less than 0, and the value at B is bigger than 0, which means there must be a 0 on this interval of length B minus A. Let's call this value L, okay? L is the length of the interval, so let's say L is B minus A. So there must be a 0, but we want to find what is the 0. So we can bisect this interval into, let's say, some point C. Then we look at the value at C. So if the value at C is 0, then we win, but usually it's false. So it's either positive or negative. In our case, it is negative, right? It's negative. When it's negative, then we look at this subinterval of half length. This has length L over 2. And then the value at C is negative and the value at B is positive. This means there must be a 0 in this interval of half the length, and then we can do it again to find. So we look at the midpoint of C and D, and let's call it D. So again, if the value is 0, then we win. But usually it's false. So in this case, it's bigger than 0. So then we look at this interval. So which means in each case, in each step, the error of the 0 is decreased by by 1/2. Okay, when I say decreased by 1/2, it means the error. Let's call the error epsilon. Okay, the error at the n+1 step is less than epsilon n over 2. Okay, because in each step, it's the length of the interval becomes 1/2 of the previous interval. So in practice, it is one way to find a 0 for some continuous function, but later we will see there is a better way for differentiable functions that is called Newton's method. Okay, we will see it later. We have to learn what the derivative is. So this is one of the application of intermediate value theorem. But in general, you can see that we can actually, the importance of 0 is only that 0 is between f of A and f of B, right? So if we can find any other value, any other intermediate value between f of A and f of B, let's say we find any value like over here, let's call this value, let's call it A, okay? That is between f of A and f of B. Then you can see if we want to go from f of A to f of B, then we must pass this point, right? We must pass this intermediate value, and we must pass any intermediate value. Which means if f is continuous on the closed interval AB And let's assume that f of a is less than f of b. And let's say we can find some a such that it is the intermediate value. Then we can definitely find some c in the open interval such that the intermediate value is attained. Okay, so this is the intermediate value theorem. Any intermediate value between the value at two endpoints, if they are not equal, is attained by some point. And clearly, there's no reason why f of a has to be less than f of b. It can be bigger, right? So if f of a is bigger than that, then we just choose any a that is between f of b and f of a. Okay. Then we still can find some c such that f of c is equal to a, right? So if f of a is bigger than f of b, it doesn't matter. Then we can still take any intermediate value. Then you can see it always have some intersection at some x that is between between these two endpoints, right? So this is the intermediate value theorem. Okay. So we can also use it in different ways, and I think it's so for now we just understand what intermediate value theorem is, and later maybe we'll do some exercises. So in the next video